Okay, so here we are for the last lecture. In the audience, there are 3 survivors and 3 online, so that's perfect. So for today, the plan is to go back to the existence, to the resolution of motion pair equation with lambda negative. I'm going to write it down. Then I'm going to make a remark while we are always working with these model potentials, so why we like them so much. And like the last thing is going to be an application of all what I presented to you. Okay, so let's start from the beginning. So from Monday, so what we want to look at, so we look at the equation theta plus I to the power of u to the power n equal to exponential of u f mu, say mu, where mu in non-pluripolar measure. Okay, so here the theorem, we look at this equation, and the theorem says that so take phi a model potential with strictly positive mass. So the mass of phi equal to theta phi to the power n over x, positive, and mu non-pluripolar measure, mu non-pluripolar measure of finite mass. Then there exists a unique u in the class E of x, theta, and phi, such that u satisfies the equation. Okay? And this is going to be like just, I recall that from last time, so from Monday, what we are able to prove is that given mu, non-pluripolar measure,
mu at omega or at omega n, or
no, this is just mu n non-pluripolar, and then if mu is f omega n with f in Lp for some t bigger than 1, then u is going to have the same singularities as capital phi. So this is for, so if you want, this is for, like last time, the Keller-Einstein equation, we got minus lambda u, and here we are taking lambda equal to minus 1. Like this, I mean, the proof is the same for any lambda. So from last time, I want to report you that given mu a non-pluripolar measure, we proved that there exists a unique, let's say, phi or v, if you want, such that theta and given mu and phi model potential exists a unique v such that theta v to the power n is equal to mu. V is in the class E of theta and phi, and the super v is normalized with 0. This is what we did last time. So the difference between this equation and this equation, that here we have this exponential term. Okay? So what we are going to use is Schauder fixed point theorem. particular, we are gonna use, so we use for the proof of this theorem here, we use a version of the shadow fixed point theorem that states that given X a Baglinian space and K a compact set in X, compact and convex, F from K to K continuous, then there exists a fixed point. There exists x in K such that f of x is equal to x. So we are going to use these results and how, so here proof. Proof of the theorem, let's say theorem, I guess the last time, I don't know, let's call it theorem B. Last time we have theorem A, theorem B. So let me write it down the space we are going to consider. We are going to consider the space K equal to the set of omega and theta plurisupermonic function more singular than capital phi as such that the integral of u with respect to omega n is equal to 0. So we are going to consider the theta plurisupermonic function that are more singular than capital phi and that are normalized somewhere. I'm not taking the normalization with the sup, but the normalization with the integral. And you're going to see why.
The Banach space is just one.
Banach spaces?
The Banach K is inside some Banach space. The Banach space is just L1.
Yes.
Okay.
So this is Banach, and then they claim that I'm not gonna prove the fact is that K is convex and compact. And compact. And the only remark I would like to make is that here it's like fundamental, it's really crucial that phi is modeled. So this is already something. Anyway, so we have this convex and compact set in a Banach space, and then we want to define this map capital F. And the map to capital F from K to K is defined as follows. So you take phi in here, and you're going to associate u such that u is in the class E of x, theta, and capital phi, and this is the unique solution of the following motion pair equation, namely theta u to the power n equal to c let me write it down. C of phi exponential of phi, yes, times mu. And here I normalize u to have u of omega n equal to 0. And here this C of phi, where I'm going to go there because I'm going to need space. So let me be, maybe let me be, okay? Where C of phi is such that the integral of tilde u to the power n, that is equal to c of phi, the integral over x of the exponential of phi mu is equal to theta phi to the power n. Okay, so let me make some remarks, or I mean at least one, like remark. U exists and it is unique because of, let me say this is theorem A, okay? Because of the theorem of the last time. Because of theorem A. Theorem A. The other remark is that here in theorem, I mean, when I studied the theorem on Monday, I said, okay, we choose the normalization sup equal to 0, but I also say that we could choose any normalization that we wanted. And here we are choosing the normalization asking that the integral is equal to 0. And they are equivalent. It's a way to determine a constant, nothing more. Okay, so and this is, you see that then theorem B relies on theorem A. Okay, so very good. You see, so let's first check that f goes from k to k, but this is okay because you take something phi in there, and then you are ending up with this u, but then the u is gonna be more singular than capital Phi because it is in this space, so by definition, and the integral is equal to 0 by construction, because we improved that. Okay, so we end up in the same case. And now, let's say, fact that I'm also, I mean, there is something to exercise for you if you want. F is continuous as well. So you have to take a sequence here of fj's that converges in L1, and then you have to prove that the corresponding sequence uj converges in L1 the corresponding u, okay, of the unit. So F is continuous. Then the Schauder fixed point theorem. The fixed point theorem. Let's say point theorem is gonna tell us that there exists phi such that f of phi is equal to phi, right? But what does it mean that f of phi is equal to phi? So f of phi was the solution, meaning that phi is a solution of theta phi to the power n equal to c of phi times exponential of phi times mu, where integral of phi with respect to omega n equal to 0, right? But this means, look at this. This means also, let's rewrite things. This is theta phi to the power n equal to, c of phi is just a constant. So we write this constant as exponential of the log, c of phi. So this is exponential of log of c of phi plus phi times mu. So rewriting things. Rewriting things, we get that, let's say, phi tilde equal to phi plus log of c of phi is such that theta phi tilde to the power n is equal to exponential of phi tilde times mu. That is exactly what we wanted. With this phi tilde that is still in the class E of x, theta, and capital Phi, because log of C of phi is just a constant. So when we do the Moser pair of phi plus a constant, it's just the Moser pair of phi. Okay? So adding a constant doesn't change the Moser pair, and here we are just rewriting the equation to get what we wanted. Okay? So, like
The
Like,
uniqueness is
the uniqueness is not like super critical. Let me see in this case. The uniqueness should be if you have theta.
Some kind of maximum principle.
Yes, exactly. Theta b to the power n exponential lambda b to the power n, and theta u lambda exponential of u to the power omega n is something like, you suppose they are different. So, for example, you suppose, I don't know, the u is strictly bigger than b, for example. Somewhere. And then you look by contradiction. So uniqueness, let's see, uniqueness. So by contradiction, we assume u different than b, and so we have that this is true somewhere. So this set here is not empty. So this set is not empty. Then we look at the other one. Then let's see. Then we look at. Okay. Yes. We look at this set. So b smaller than u. So it's the same. I just by routing in the other way around. So this is theta u to the power n. Then this is less or equal thanks to the comparison principle. So CP for comparison principle. B less than u, theta b to the power n, but this is equal to over this set. So this solves the motion pair equation. So this is this, and this solves the same.
Omega is you can take also mu. Omega to the n or mu.
Yeah, mu is the same. But let me take omega to the power n just to review the idea. And this on the other side is on the set. This is this is exponential of u omega to the power n. Do you agree? Here, this means we then found that the integral from b to u of the exponential of u minus exponential of v omega n has to be less or equal than 0, right?
Okay.
Yes. But on yes, on the set u strictly less than u, we have that the exponential of v is strictly less than the exponential of u, because the exponential is increasing, right?
Okay.
I mean, strictly increasing actually, and so this means that this quantity is strictly positive. But then saying that the integral is negative, it then means that the set has to be empty.
I know, or measure 0. No.
Yeah, with respect to the bag.
Okay.
But if you get it's with respect to the bag. If you respect mu, you have that mu of this is equal to 0. It means that this guy is equal, has to be a pluripolar set. Because this is not pluripolar.
Well.
Yeah, more or less. I mean, either is 0 with respect to the bag, hence the set is empty. Otherwise, it's going to be a pluripolar set, but then it means that u is greater or equal than b outside a pluripolar set and everywhere, because there are two quasi-pluripolar functions.
Yeah, well, but we know that any pluripolar has measure 0, not that anything has measure 0 is pluripolar.
No, of course, but then if you do so the measure, so here if you have the measure
of this guy is 0. So I guess you have to compare mu with some capacity, maybe. No.
Yes, so you will do that. Again, as they say, you write mu as f on mu, where f is in F1 and mu of mu, and mu is dominated by the capacity.
Ah, okay.
And then you can do the same. Okay. Okay, this was for the uniqueness. So the uniqueness in the case with the exponential just follows from the comparison principle. You see, we just use the comparison principle this level. The other side is just the equation. And we arrive at we assume by contradiction that this set was not empty, but then we prove that this set has to be empty. Okay, so this was for the version with exponential. So we treat the case lambda equal to 0 and lambda negative. So theorem A and theorem B, so especially I'm going to give you a corollary. Maybe I can leave it here. So here. Corollary is the existence of Keller-Einstein matrix with prescribed singularities. And in particular, I'm going to give a statement for the case lambda negative, okay? So the precise statement here, but the analogous one holds for lambda equal to 0. But let me make it. So we take x that is with canonical the canonical line bundle ample. So x with C1 of x negative. So x is smooth, okay? Smooth with C1 negative, namely that the canonical is ample. We consider H an emission metric on chi x, so we fix, we consider most fix with E over 2 pi with a strictly positive curvature. And we can do that because the canonical is ample, meaning exactly this. And we call this curvature here, we call it theta, okay? So it's gonna be our theta all along. Very good. Then fix phi in model potential. So theta Pluri supermonic function such that its envelope of singularity is equal to self and with positive mass. Then we can infer that there exists a unique Keller-Einstein metric given by the potential capital phi K A. So let's say a unique Keller-Einstein metric that is going to be of the type H times exponential of minus phi Ka, on Kx with the same singularities of capital phi, the potential we started with. So what does it mean? I mean, here I just I wrote the metric on the canonical, the emission metric instead of the form. But the form here, so what does it mean being a Keller-Einstein metric? It means that phi Ka, the potential, is the unique potential solving the following equation. So we ask that theta plus I to the power of phi Ka to the power n is equal to the exponential of phi Ka times f theta omega n, where f theta is always the local potential of the Ricci. So this is theta n, but theta is scalar, and such that phi Ka has the same singularity type of capital phi. This is exactly what we proved in theorem. This is exactly theorem B. There. Okay?
But you really need ample or big is sufficient? Okay, yeah.
No, I guess the big is sufficient. But just I wrote it down the algebraic geometric version of general type. Okay. Good. And then the same, remark, analogous result for Calabi-Yau. Analogous for Calabi-Yau method. So this is the case lambda equal to 0 case. So what we proved, we really proved at the end of all these lectures is that when the first rank class is negative or equal to 0, then given a potential, so prescribing like a singularity at the beginning, I can always find a unique Keller-Einstein metric with that behavior, with that singularities. Remember, Yau's theorem said, I have the Calabi-Yau manifold, the general type, I can find a smooth Keller-Einstein metric. Here, I'm going to find a singular Keller-Einstein metric with any singularity, model singularity that I choose at the beginning. So it's really like a generalization of that. Okay. Good. So this was like to really like to give you an idea of how powerful is this pluripotential theory. So whatsoever. Now, before the application, I would like to make a remark on why we always start with this assumption model, because it could seem you could think that like this is an assumption that we need, like it's sufficient but not necessary. And now what I'm going to show you, that actually is really necessary. Otherwise, the equation is not well defined. I'm dying. Okay. So here the remark goes as follows. So remark, the assumption model potential is necessary, not only sufficient. As the theorem ensures. So we take phi with positive mass, so just theta SH with positive mass, and we assume that for any bounded function non-negative, there exists a solution to the problem theta u to the power n equal to f omega n with u having the same singularities as phi, and then you can also normalize with soup equal to 0 to get the uniqueness. So we assume that. So you fix phi, and then you say any time that you take a bounded function, then you can always solve the equation with u as singular as phi. Okay, so we assume that, and what then it follows that phi has to be model. Model, namely that phi has to be equal to p, the envelope of singularities of itself. So this is what we are gonna prove. Okay? So in this sense, the assumption is necessary because otherwise we do not solve. Okay, here we are. Proof. So we have all the ingredients for the proof. So let's do that. Proof. By contradiction, the proof goes by contradiction. We assume that phi is non-model, and this means that when I do the envelope of singularities, so let me drop the theta here, okay? I'm not going to write the theta, but just it's always the envelope with respect to theta, is strictly less singular than phi. So I'm going to write P of phi less singular, so strictly for this, or capital phi. Okay? They cannot have the same singularities, otherwise phi would be model.
Okay.
Because like here it is, but being model also means when so maybe this is better. When I look at the difference, this has to be bounded, because the modeling means that phi and p of phi are in the same singularity class, so that the difference is bounded. So if phi is not modeling, it means that this guy is strictly less singular than this guy, so the difference is not bounded. So this is all I am saying. Okay, and this means that if I look at the class E of x theta with respect to phi, and I look at this other class, I do have an inclusion that goes like this. I have a strict inclusion. Why? Because this set is defined as all the functions, they are theta VSH less singular than phi and with the same mass. Right? But if I take such a u that is less singular than phi, then u is less singular than phi, and phi was more singular than p or phi, it means that u is more singular than p of phi. The inequality goes in the right direction. And also, the mass of theta u is equal to the mass of phi, that is also equal to the mass on the envelope. So this is what I proved, right? The mass of the motion pair of phi is equal to the mass of motion pair of the envelope. So we have this inequality like this, strict inequality. The inequality is strict because p of phi is not in this class, because it's not less singular than phi.
Okay.
Okay?
P of phi is in E of P of phi, but it's not.
Yes. So let me write it down, okay? So maybe here. observe that the inequality is strict because P of phi is in the class P of x theta P of phi, but not in the class P of theta phi. Okay? Because it's not less singular than phi. Okay, good. And now, so I remind you, so I'm gonna tell you a fact that I already used like a couple of that lectures ago, maybe like first lecture before after Christmas. And the fact that actually we proved with Stefano, I guess it was 2020, maybe 21. It says that the motion per mass of the envelope is supported on the contact set. And on the contact set, the form theta is positive, not negative. So using that, so then this means that we can rewrite, so this mass, it can be written as f omega to the power n, where f is a bounded function, right?
Theta or omega?
No,
Theta, no, omega.
No, you can write also omega to the power n. This is going to be a volume, a positive measure of this set, and then you can compare it with the Lebesgue measure.
Okay, and this will be bound.
This f is going to be supported here,
okay.
And it's going to be also such that theta n is equal to f omega n on this set.
Okay.
And this is bounded.
Yeah. Okay.
So f here is defined in such a way, so it's 0 outside this. And it's going to be such that f equal to f, such that theta n equal to f omega n on the contact set.
Yeah. Okay.
And this is possible because this on the contact set this is a positive volume form, and this is also positive volume form. So I'm comparing the two. So just why I say that theta is positive on the contact set, so observe that theta is non-negative in P of phi equal to 0, because, so this is very naive, but because we know that theta plus IBD bar of P of phi is positive. This is the condition of the theta plurisupermonicity. When P of theta is equal to 0, this term is not there. So on the contact set, it means that theta is positive. Okay? This is just to give you an idea. It's not the formal way to argue, just to give you an idea. Anyhow, so look at what I have here. I have that theta and the motion pair of Pn can be written as f omega n with f bounded. But then, and this is also P of capital phi is the unique solution of that motion pair equation. This is because of the uniqueness, right? But then this is a contradiction. This contradicts. So this here. This contradicts the assumption of the theorem. Because given f bounded and non-negative, the assumption says that we can solve theta u to the power n equal to f omega n with u with the same singularity of phi. But here, the solution of the equation is u equal to p of phi. And p of phi has not the same singularity as phi because we started by contradiction. So this means that we are out of contradiction. Okay? Contradiction with assumption.
Good.
Like it? Okay. So this was really to make you believe, in a sense, that the assumption of the model was something that was a sufficient and necessary condition. So we really need to work with this model type singularities. Okay, so now I guess that I proposed, and I don't know if you agree, to not make a pause. I'm gonna go with the application, and then when we're gonna finish, we're gonna finish. Okay, application. So it's a game. I really hope you like it. It's really a game. Let me just rewrite it down. Theorem A here. Recall, okay? Here. So the theorem was to say that if I take f in a p for some p bigger than 1, capital phi model, such that the mass of f omega n is equal to the mass of phi, strictly positive, then there exists a unique phi with the same singularity of capital phi, solution of theta phi to the power n f omega n. So let's say that this is a particular version of theorem A, because theorem A was stated for any pluripolar measure. Here I'm taking this neither one, but this is all we need. So the statement, the application that I would like to present you is the log concavity of the volume. So application of the resolution of Montampere equation with the prescribed singularities is the log concavity of the volume. So what do I mean by that? So let me now we take theta 1, theta n different, n possibly different big cohomology classes, big forms, let's say, meaning that when I take the class, the cohomology class is big, and then I take for each of these theta j, I take u1, un, such that each uj is ESH with respect to theta j. So the only thing I want to say is that I can take n different classes and n different functions. Okay? So it's really, really general. Then let me write it down for each j, also because it's better for the notation. I write T of j, this is defined as theta j plus I d bar of uj. And this was something positive, right? Because this guy is theta j VSH. Okay. Then the statement, the log concavity of the volume says that then the log concavity of the volume says that the integral over x of T1 wedge T2 wedge T3 up to Tn is greater or equal than the integral over x of T1 to the power n 1 over n times T2, the same thing with T2 up to Tn. when you see T1 to the power n, this is just the Mojampere measure of theta 1 plus I to the bar of U1. This is just, so this is called, this is known as the log concavity of the volume. Why? Let me make a remark before starting also with the an historical note. One can see it's not like difficult, I mean, just a computation, that this, let's call it the star implies that the function that to theta u, so theta plus I to the bar of u, is going to associate the integral over x of theta u to the power n to the power 1 over n is concave. Or equivalently, that the map that to theta u is going to associate the log of the integral of the theta u to the power n is concave as well. And this is why the statement is known as the log concavity of the volume of the mass. Okay?
This is that statement is
that statement, no, that statement implies this, and
okay.
these two are equivalent.
Okay.
That one is stronger. Okay, so now maybe the historical note. So history. This theorem was known in the case when theta, the class theta, I mean in this version, the class theta is big enough. So I have an extra assumption, whatever net means, and this was proved by Favre and Johnson in 2009. And was also proved by Buxom, Sedieu, Gage, and Zeriai in 2010, when all the uj have a particular form, namely they have analytic singularities. So the uj writes as a small constant, positive constant, times the log of the sum of some functions, holomorphic functions. Here there is the dependence on j, so these are holomorphic, plus a bounded function, okay? So they prove this statement in a very particular case. The general case, so any singularity or a function with any singularity was not known, and this was one of the, this was known as the log concavity conjecture. So with Tamash and Chin, we saw this conjecture that was open from 2010. So the full conjecture was proved by us, so DDL, in 2020, so 10 years. And now I'm going to give you the proof. And the proof once, like the technical thing, the crucial thing, it was to solve Mojampere equation with prescribed singularities. Once we have done that, this is a game. So my goal is really to show you that the proof of this conjecture, it's like it's very simple once we know theorem A over there. Okay. No, maybe I'm gonna start here and then I'm gonna go up there because I would like to leave the statement for a while. Okay. So proof. Proof of star was the log concavity in the conjecture. Star is the inequality. So first, what we do, we assume that up to normalization, we can always do that. We assume that the integral of omega n is equal to 1, and also like all the masses of Tj to the power n are equal to 1. All these masses are 1. We can always do that because we can normalize. So let me rewrite down the inequality. The inequality says that this guy has to be greater or equal than 1 because all of here are all 1s. Okay? So here I write 1. Okay? We can assume that up to normalization. Up to normalization. We can just divide by the mass. Okay? So not really nothing serious here. Okay, so we get this theta uj, and remember that theta uj was of the type theta j plus IDD bar of uj. Okay, so now uj, as I said, can have any singularity. It can be. We just know that it's theta j psh. But now we are gonna. So given uj, we construct its envelope of singularity, p of theta j. Right? So we construct this. We construct this envelope of singularities, and then theorem A H says that, in short, that there exists, so for any j from 1 to n, there exists a unique normalized with sup equal to 0 phi j that is in the class E of x theta j of what? Of p of uj. So where the envelope is always done with respect to the right form. So the envelope here is done with respect to theta j, the reference form. There exists a unique phi j solving in this class E, solving theta, let me write it down, theta j plus I dd bar of phi j to the power n equal to just omega n. So here we use theorem 1 with f identically 1. Okay? And of course, f equal to 1 is an NP for any p that you want. Okay? So we can solve. Because using the fact that this guy is model, this is the model potential. Okay, so now we have this phi j, and what we do with this phi j? So we observe, we remember that by construction, the mass of this so theta j phi j to the power n, the mass of this guy is equal to the mass of this, of the P, the envelope, that was also equal to the mass of theta uj j to the power n. So here it's becoming complicated with the don't look at the reference form. The reference form is the right one, but here we are saying that the mass of the motion pair measure of phi j is equal to the mass of the motion pair of the measure of the envelope, because this function is in the class E, and the mass of this guy is equal to the mass of uj, and this is something that we proved some time ago, I don't know when. Okay, and also with the same, so this is true for any j, okay, and from this you can kind of believe me. I could also prove it, kind of if you just with the notation, that this implies that if I have this equality for any j, I also have that theta 1 phi j wedge theta 2 phi 1, theta 2 phi 2 up to the last one. This is equal to the mass of these guys when I do the wedge, the different wedges. Theta 1 u1, theta n un. So why is that? This is just the multilinearity of the non-pluripotent. for that product? It requires some time, you have to be difficult. All I want to say is that if you know that this at any j I have the mass that is equal, then I can do like a mixed version if you want. This is the mixed version. Say that. So here, at any time, I can replace with the function I started with. So if you want, it goes like this. At any time, I can replace with the envelope of singularity. So this is the right, maybe the right way. And the envelope of singularity I can replace with the function I started with. So I'm just saying that when you have the full version, you can also go back to the mixed version. Okay, but then we are done. We are done because, so remember this is what we wanted, okay? So we wanted the theta, so this was theta j u1. So let me write it down maybe here. This was equal to, this guy, just my notation, was equal to theta 1 wedge theta n, okay?
Which one?
The last guy was equal to this, just by notation. Okay, but let me write it down here. So let's see what we have. So we have, up to now, we have the integral of theta 1 theta n with my notation is equal to what we had there, the integral of x of theta 1 phi 1 wedge theta n phi n. Okay? And we also know that for any j, so we have this, and we have that for any j, theta j f j phi j to the power n is equal to omega n. Okay? So this is what we have done in structure. Now we are going to use some facts in pluripotential theory, a very general one by DiNezza, 2009, I guess. So, and the fact says that if I have theta u to the power n that is equal to f omega n, and theta b to the power n that is equal to g omega n, then the mixed motion paired mass theta u to the power k wedge theta b to the power n minus k, so this is the mixed mass, is greater or equal than f to the power k divided by n. So this I'm taking the power k, and for this I'm going to take the power g n minus k divided by n times omega n. So these are called like the mixed motion pair inequalities. Okay? Mixed motion pair inequalities. Okay, now look at this. So using that fact to I take all the different now. I mean, this can be generalized with n, with f1, f2, fn. Using this fact, I have that theta 1 f1. So the fact there tells us that theta 1 phi n wedge theta phi 2 wedge up to n is greater or equal than what? Okay, let's look at that. So anytime f and g are all 1. Right? So here in the fact with f equal to g equal to 1. So here I have that this mixed measure is greater or equal than 1 times omega n.
But for example, if you have 3 of that kind,
yeah, it's the same. So,
so
let me write it down. Let me write it down like this. Maybe you like it better. This is theta j. This is fj. Then theta. Then theta u1 wedge theta un is greater or equal than the product of f, yes, over fj,
Okay.
to the power 1 over n. Each one is to the power 1 over n. Okay? Maybe it's better like this. I mean, it's the same. You can recover this from what I say. Now we're going to use the fact with fj is equal to 1 and uj is equal to phi j. So this is going to be greater or equal than the product of 1, that is 1 times omega n. Is that okay? Okay. But now, if this is true at the level of measure, it's true also if I do the integral. Right? But this was equal to 1 because we normalized that, right? And this guy here is equal to this. Hence, we prove that the integral over x of t1 over h blah 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 up to tn is greater or equal than 1. That is exactly what we wanted to do. And this is definitely so.
Of the story. Okay.
So, like the proof of this, I mean, of course, it uses the resolution of motion pair equation which describes singularities, and also like all the theory we developed with this envelope of singularity, the fact that the mass are equal, so on. So, but it always uses the same instrument, let's say. Okay. Yeah, I guess it's a good time to stop. If you have questions. I dropped a lot of things, so I'm happy. People on the web, do you have questions?
I'm fine. I'd just like to thank you enormously, Eleonora.
Coming every time. Thanks a lot.
It was really interesting. A little bit out of my area, but really interesting. That last. Yeah.
I did a lot, so I'm happy, but I hope that you were not scared. Okay.
Yeah.
Ciao Armando.
Ciao, ma poi ti scrivo.
Sì, volentieri.
Ma sei ancora a Roma questa settimana?
Parto sabato.
Ok, allora scrivo subito.
Va bene. Ciao.
Grazie. See you. Bye.
Ciao.
Thank you.
Ciao Andrew. Ciao guys.
Bye bye.
Bye bye. Abbandono.
So thank you very much to everyone that organized the course. Ciao.